Hi, this is the second of three videos that I'm using to explain how to solve equations where you have trig functions. So effectively trying to find a missing angle or angles, depending on how many solutions that we might have. And you can see this is a much more complex example than we had in video one. And if you haven't watched the example one video, then I suggest you do go back and have a look at it because I'm assuming you have watched it when I talk about the stuff in this video. Brief reminder though is that we have these two trig identities. It's expected that you have seen these before we tackle this video. We've got tan theta equals sine on cos and sine squared plus cos squared equals 1. And a reminder that what I said to you in the previous video is that although these are the way the identities are written, you can reorganize these equations to suit you. And you're going to see that in the example that I've got for you now. So what do we need to look at here? Ultimately, when it comes to trig equations that we need to solve, we want to do what we really want to do is we want to get one of the sides of the equation so that it is a trig function by itself with some sort of value in the inside and then equals some sort of value on the right-hand side. That's what we want to do. While it's like this, we can't do much with it. We need to have it like sine of blah, blah, blah is equal to blah, 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 that kind of thing. The other thing that's really important to note in a trig equation that you need to solve is the domain. In this case, the domain is x is between or equal to 0 and 2 pi. So that tells us what the range or what the possible values could be. I don't need to look outside of 2 pi or before 0 for my solutions. So let's get into it. What have we got? We've got 2 cos squared x plus sine x. And the first thing we'll want to do is we want to try and eliminate multiple trig functions here. I've got cosine and sine here, and that's not going to be particularly useful to us. We want to really make sure that we've got only one. When we look at the two basic trig identities we've got this one where I could say sine theta equals tan theta times cos theta. And although that means I could get rid of the sine theta and replace it with cos tan, then I've still got cos and tan, so it's not any better really. But look at this one here, sine squared plus cos squared equals 1. If I say sine squared equals 1 minus cos squared, then I can replace a sine squared with 1 minus cos squared, right? Having a look at the problem, I don't have a sine squared. Whoops, can I say that again? If I have cos squared and I subtract sine squared onto this side, I would have cos squared equals 1 minus sine squared. So I've got a cos squared here, so I can literally replace the cos squared x with 1 minus sine squared x. So we've got 2 outside of 1 minus sine squared x plus sine x is equal to 1. And this is good news. We've now only got one trig function to deal with, but it's still found in multiple places when we really need it to be sine of something is equal to something else. So let's keep on going and see where we go. I'm going to expand the brackets. So I've got 2 minus 2 sine squared x plus sine x is equal to 1. And then I'm going to do something which is not something that you may intuitively get to do. What I'm going to do is I am going to add everything onto the right-hand side so that I've got an equation equal to 0. And then I'm going to flip it as well. I'll show you what I mean. If I add 2 sine squared x to both sides, then I'd have 2 sine squared x. Yes, it would be on the other side, but we can deal with this, can't we? Then I'd have to subtract sine x to both sides, so I'd have a minus sine x. Then I'd have 1 minus 2, and that would give me minus 1. And then I'd have an equals 0. Now, in mathematics, this is a pretty common thing to do, to create an equation that we can set equal to 0 so that we can hopefully use something like the null factor law or quadratic formula or something in order to solve the equation. And that's exactly what we're going to do here. Now, what I'm about to do is something that the textbook doesn't do, and the videos that you watch, not everyone does it as well. But I find it a really useful step. I'll show you what I'm going to do. Well, let me sort of explain what we've got here first. What we've got is we've got 2, and then we've got a sine x that is squared. Then we've got a minus, and then a sine x again, and then we've got a minus 1. If we can sort of look beyond the sine x and know that sine x is just a variable, say, for example, because whatever x is, sine x will change as we go along, but we can change the value of x and that will change the value of sine x. So sine x is effectively like a variable. So we've got 2 times the variable squared minus the same variable in the middle minus 1. And doesn't that feel like a quadratic? But instead of being x squared or t squared or q squared, it's sine x that's been squared. So I'm going to go this is what's different from the textbook, let a equal sine of x. As usual, I'm not using the bracket notation just to keep my solutions as clean as possible. What would we then have? We would have, not therefore, then a squared minus a minus 1 is equal to 0. Can you see what I've done there? So instead of 2a squared. So instead of having 2 sine squared x, we've now just got 2a squared. Instead of sine x, we've now got a. So we've got this, and this looks much more comfortably like a quadratic that we've factorized before. I'm going to use the diamond method to factorize this, and if you're not used to the diamond method, then this might seem a little bit strange, but use whatever method you want to factorize this. And if you can't work out how to factorize it, this one is factorizable, but some aren't, then you might use the quadratic formula at this point. But we won't use the quadratic formula here. We'll just use the diamond method, and the diamond method does this: multiply a and c together, so that gives me minus 2. And then underneath it, I put the coefficient of a, which is b, minus 1. Then I circle this bit, and this tells me the information that I need right now, which is I need to have 2 numbers that will multiply together to give me 2, and that minus says 1 apart. If that was a plus there, I'd say it would add up to 2, but in this case, minus means 1 apart. Okay, so that would be, let me see, 2 and 1. 2 times 1 is 2, and 2 and 1 are 1 apart. So there's our 2 numbers there. And they form denominators of some fractions. I put the minus sign that I haven't circled on the biggest one because I need to get to minus 1 ultimately. So it's going to be minus 2 and plus 1. Then I take the 2a squared and get rid of the square, and that leaves me with 2a on top and left and right here. And then I can see there's a common factor of 2 here that I'm going to cancel down. So 2a squared minus a minus 1 is a minus 1 and 2a plus 1 equals 0. And I shouldn't be putting an equal sign there. Okay, so that's what we've got so far. A minus 1 times 2a plus 1 is equal to 0. So by the null factor law, a is equal to 1, or a is equal to minus a half. So there are our 2 solutions. Okay, now I'm going to return it back to what we're looking for, which is we're trying to find what x is, not what a is. So what is a? A is sine x. So therefore, the sine of x is equal to 1, or the sine of x is equal to minus a half. We'll tackle them separately, because otherwise it gets a bit confusing. So what does sine of x equal to 1 mean? Well, this is when we return to our unit circle axes like so, say, well, where is the y-coordinate equal to 1? And the answer is right there. It's equal to 1. Remember that the unit circle is a line that goes 1 unit across. So here, sine of x is equal to 0. Here, sine of x is equal to 1. Here, sine of x is equal to 0. Here, sine of x is equal to negative 1, but we've got positive 1 here. And everything in between is a value between there. So between 0 and 1, between 0 and 1 here, between 0 and negative 1 here, between 0 and negative 1 here. Okay, so it's exactly equal to there. And what angle would that make? Would that be? That would be pi on 2. So there's sine of x equals 1, giving us a value of x equals pi on 2. Or the sine of x is equal to negative 1/2. That was the other value that we had up here, a equals minus a half. Okay, so what do we do with that? Well, we need to think very carefully again. We'll put our unit circle axes on here, and we can see that sine is negative, or the value of the sine is negative. So where is sine negative? All students take care. All sine, tan, cosine. So only tan and cos are positive here, which means that sine is negative here and sine is negative there. So that's where we need our angle to end up. I can draw it as a little line here, like so, and I'll use a different color for the line here, just so we can get a sense of it. So x is either going to be this angle or x is going to be this angle. And again, I cannot emphasize enough that the diagram that you draw is an excellent visual aid and means you don't have to remember lots of meaningless kinds of relationships, like sine of x, pi minus, sine of pi minus theta equals sine of theta, that kind of thing. So what we're interested in, as per usual, is the angle between the x-axis and the line, and that's our reference angle. It's that acute angle. So we go sine of x hat is equal to a half. We ignore the sign and SIGN. We ignore whether it's positive or negative and just say, what is that reference angle? And where is sine of x? Where is sine of x hat equal to a half? Pop my triangle in. This is going to be my equilateral triangle here. So I've got 60 degrees here, pi on 3. I've got 30 degrees here, pi on 6. And this is 1 here. This is an equilateral triangle, so this is going to be a half here. I'll zoom up so you can sort of see it a little bit better, maybe. Nice and big. And that's root 3 on 2. Not that we care because it's not what we're looking for. So there we go. I can see that because sine is opposite, it's a half is opposite pi on 6. So I can see that x hat equals pi on 6. That's the reference angle. Off to slide 8 here. I'll zoom out so you can see the whole thing again. So we've got the reference angle being pi on 6. So that basically means that this little angle here is pi on 6 and this little angle here is pi on 6. So if the actual angle, so let's have a look at the red one to start with, is from here to here, well, that's going to be pi plus pi on 6. So we can say, therefore, x is equal to, and let's do this in our heads, pi is 6 pi on 6, right? So if we've got pi plus pi on 6, that's going to be 6 plus 1 pi on 6. So it's going to be 7 pi on 6. For the next one, it's all the way around here, which is basically a full rotation minus this bit here. So we've got 2 pi minus pi on 6. So 2 pi is 12 pi on 6. So we've got one less than that. So it's going to be 11 pi on 6. And if you want to be a bit fancy, you can put it all together, i.e. x is equal to pi on 2. That's one solution that will work. 7 pi on 6. It's a second solution that will work. And 11 pi on 6. And they are the only three solutions we need because we're told that the x values are between 0 and 2 pi. So although we could find more values for x, they would be either less than 0 or they would be bigger than 2 pi, so they don't count. And that's basically it. In the next example, we're going to have a look at an even more complex example. It's not quite as tricky in terms of the manipulation of algebra here, like we had to do here, but there are, in fact, more solutions than I've got here. So we'll cover that in the next video.